All right, so today we'll be talking about program synthesis with large language models, and it's done by Google Research by Jacob Austin et al. Um, what is synthesis? It is building programs from unstructured program specifications. Specifically, it's been a problem uh, standing goal for AI research, and AI researchers have tried to tackle this problem across the ages. So previous work in program synthesis tends to focus on symbolic and near-symbolic methods earlier on in the day. The paper also mentions that applied that it's mainly applied to domain-specific languages, um, which restricts. They claim that domain-specific languages tend to restrict possible applications, and since the problems are domain specific, they don't uh, go across domains. And if we are able to do program synthesis across different domains in a general programming language, it can help the workflows of expert and novice programmers. Oh, um, why large language models for program synthesis? The authors claim that, well, uh, large language models tend to generate natural language text well. They are also have been tested for their ability to solve reasoning tasks, such as question answering, and they tend to do really well on those as well. And more recently, large language models such as CodeBERT and PyMT5, and more recently Code.AI, have been applied to generate source code text. Um, w- with the availability of really large data, um, the authors claim that there may not be a need to encode the grammar of a specific programming language, because given enough data, the large language models would be able to infer the syntax of programming languages as well, similarly to how they have been able to generate coherent, or at least syntactically coherent or grammatically coherent natural language text for like English. Um, Furthermore, large language models read and train on human code, and hence they're able to generate more human-like code as opposed to something symbolic. Um, Furthermore, the program specifications, the input to the program synthesis model, um, can be more flexible with large language models. We can include natural language text or descriptions, and consider few-shot input-output examples for the program specifications instead of like logic constraints or strictly input-output examples. Okay, next slide. Okay, the paper. Sorry, I have to click on Discord as well to make sure that it's still screen sharing there. Um, The main contributions of this paper are they introduced two new program synthesis datasets. The MBPP, mostly basic programming problems, which is around 974 entry-level Python function codes associated with natural language descriptions and test cases. I'll go over an example later. Um, these dataset contains a lot more control flow statements in Python, like for loops and if statements. Um, and as opposed to the other one. The other dataset is the MathQ question answering Python dataset, which is there's another dataset called MathQA, which is done in a domain specific language. And this is converted to Python, and it contains about 23,000 or 24,000 programs and Python synthesis problems. And the key thing about this dataset is it contains complex natural language descriptions as opposed to the earlier dataset. The other contribution is the authors claim good results with few-shot learning only. So without even fine-tuning their large language models on these datasets, they are able to get really good results. They mention, uh, sorry, I'm trying to find the page. They mention 59.6% of MBPP uh, was able to be solved using only few-shot learning. And few-shot learning here means that given the natural language description, you're giving it 3 input-output examples um, for that specific task. Um, and the other data set, they claim it's a bit more difficult. Few shot accuracy is about 33.4%. And fine-tuning all the large language models they achieve about an increase of 10%. Um, so when fine-tuning, my understanding is that they don't include input-output examples. It's only the NL descriptions. And when they fine-tune, it's 10% above uh, the top-performing few-shot learning model. Okay. The third contribution is something I saw this somewhere on Twitter, conversational programming, and I really like this term. And they study the model's ability to engage in dialogue about the code and adapt to the feedback the human gives in natural language, which I found really interesting. Which begs the question: are the models able to understand the code that they are seeing? And the answer seems to be no. There seems to be still a gap between generation and understanding. The test for this was the models were tasked with predicting a program's output. There's a grammatical issue there. Um, and the results don't seem very promising in that aspect. There's also an ablation sensitivity analysis study, changing the model size, examples in the output, identity examples, and different sampling techniques. And we'll go over these in a bit. Okay, next slide. Okay, so here's an example of the mostly basic Python programming problems dataset. Um, we noticed that there's a natural language description on the top, if my cursor is seeable. Write a Python function to check if a given number is one less and twice its reverse. And then the test cases are the few shot examples. So um, if the parameter is 70, the answer should be false. If the parameter is 23, it should be false. If it's 73, it should be true. And this is the answer, or the output generated by the model. And the examples can be a bit more complex, so doing like something like merge sort, and so on. Okay, next example. The Math QA Python dataset contains the domain-specific language, but you can see it's a lot more complex natural language intent. In this, well, it doesn't seem more complex here, but in terms of understanding it, it is. Solve a mathematical problem. And you're given some parameters, and these are sample outputs. So they're providing us with 3 sample outputs here. And the equivalent, and the Python model solves it this way. By putting in n0 here, n1 here, n2, n2 is missing, n2 here, and n3 here. And the task is to predict the answer and solve this mathematical problem. I think T1 is, oh, and the equivalent DSL code here is add n1 and n2. So T0 equals n1 and n2. And then you'd want to divide n3 by T0. T0 is the previous, and then you'd want to store that in 1, and then you add n0 and n1, and that's the answer. And so these 3 steps are the answer. Okay. I think I want to correct something. These are the initial parameters from the NL problem. The few shot isn't given. I'm not sure how their few shot is, or the input output examples are done, but there are input output examples as well. Okay. Next example. Okay, so for the approach, the researchers have used, they don't mention GPT, but they mentioned that they've used decoder-only models, left to right, transform, and they cite the Transformers paper. And they scale their models sizes from 244 million to 137 billion, and they do an ablation on that. And their pre-training data, I think they're pre-training these models from scratch. It contains about 3 billion documents, and 13.8 million uh, of these documents are from websites with code, such as Stack Overflow or like tutorial websites like Geeks for Greeks or something. Geeks for Geeks or something. And how they went about evaluating this, uh, at least for the program synthesis portion, is that they have these two settings. They have the few shot prompting, so they add in those input and output examples. Similar, the few shot learning is similar to GPT-3, but the prompt is basically like input and output examples, as shown earlier. And then the second setting is you fine tune on the training set. And notably, the training set for MBPP is very small, only 374 examples. For the evaluation, it's simple. They don't use Blue Score or any text-based metrics. If it passes the test case, then it's correct. Otherwise, it's incorrect. For math, so similar to the human eval dataset by OpenAI. The math QA, they generate 80 samples, and these 80 samples are evaluated against the test cases. For MBPP, they mentioned that they only generate one output and they check the exact output against the use cases. So only one program, and they check it against the use cases, which threw me off a little bit, and you'll see in a second. Okay, next, the MBP results. So the graph on the left, so the x and y axes first. The x-axis focuses on the model size and millions of parameters, and the y-axis focuses on percent of tasks solved by that model. On the left portion is how many percentage of tasks solved, and on the right is percent of samples solving the task. So I'm assuming the model will generate many samples. In the previous mentioned 80 samples in the previous slide, but these results are only for the MBP dataset. So it's a bit, I didn't quite capture that. So that's a bit confusing. But yeah, percentage of samples generated by the model that solved that particular task. And so the conclusion is synthesis performance scales log linearly with the model size. And fine-tuning does better than few shot by a bit. Okay. And the next set of results focuses on the model size. The task index is merely an ID for the task, sorted in ascending order by um, how well the model does on that task. And so 500 is generally done well by the models, or it, yeah, generated good samples by that models. The main conclusion is, sorry, the left figure shows the results for few shot prompting. The right figure shows for fine tuned, and generally the curve is pushed up and to the left by the area under the curve increases as parameters are added to the model. Because of that up and left motion, the blue is higher than the pink, for instance. We notice that the bigger the model, the better it does on all of the tasks. And that's the main conclusion here. And there isn't that much difference between few shot and fine-tuned. Bigger models generally do better. Okay. The other set of results is studies how many prompt examples are given. So in the few shot, so 0 shot means no examples. 1 shot means one input output example is given, and so on. And we noticed that the sweet point is 2 examples for the MBP dataset. 59% of the problems are solved. But interestingly, 43.2% of the problems are solved with no examples. And I'm assuming this is without fine-tuning either, which is interesting. Percentage of samples solving the tasks. Yeah, that is a bit tricky. I didn't quite capture it, but perhaps I need to reread it. Um, yeah, and so another conclusion that I wanted to mention, but isn't in this figure, is that they also did some analysis of the errors, and they consider runtime errors as non-syntactic errors that cause the program to crash or not execute. Um, and for most model sizes, runtime errors are more common than syntax errors, which relates to the original hypothesis that large language models are able to syntactically learn the syntax of a programming language. Um, and about 80% of the time, it's correct Python code or is syntactically compilable. But again, Python code doesn't have a lot of syntax kind of constraints as other languages like C++ or Java. And so that's something to also consider. Um, duh, duh, duh. For the largest model, over 63% of all failures are due to failing test assertions as opposed to runtime or syntactic errors, which is also a good thing. Okay. Um, so this is the breakdown of error types. And we can see that the bigger the model is, the higher the green portion. On the left figure, I'm looking at figure 5. So test cases passed here. Oops, I need to. So test cases passed here are higher, the bigger the model is. Tests failed are larger in this area. Runtime errors here are less as the bigger we go, but significantly lower here, but we also have a lot of tests failed. So we can see that the model is trying to optimize. The bigger it is, the more comfortable it becomes with solving the tests correctly, and the less runtime and syntax errors it has. But type errors still seem to be a problem either way, which relates to the idea of like, is it really understanding? Okay. Um, so on the right side, performance is a function. Um, sorry, I don't remember what seed is. Okay, the seed label corresponds to random seed chose. Oh, so they just randomized it. Um, and then they redid their analysis with different seeds. And it seems, but I'm not sure why it's higher. The percentage of tasks solved is higher. Whoops, what did I do? That was my last slide. Okay. Oh, they are ordered by. Okay, so there is no relation. The seeds are ordered by the fraction of tasks solved by that seed, but it's still an interesting phenomenon to see that. I guess randomizing the test set or held out examples uh, has some pretty significant relationship with the percentage of tasks solved, which may indicate overfitting. I'm not sure. Okay, that's the slide deck, but we have a lot more results that I didn't have a chance to cover here. Mainly okay, so we stopped here. Right. I need to reread this section because I didn't understand this figure actually. Okay, solutions typically generalize to held out test cases. That's the conclusion they had. Um, but I'll probably just jump to, oh, and another conclusion they had is sampling strategy is critical for good performance. They tried different sampling strategies, temperature with ranked temperatures, and beam search. Sorry, am I screen sharing the paper? I don't think I am. Let me do that. That's what. Da, da, da. Change windows. I guess I'd have to redo it. Ah, there we go. Okay. Okay, so um yeah, so the first conclusion is solutions typically generalize to test out cases. Um, and I need to reread this section because I'm not sure I understood this figure. It was a bit confusing. Um, yes, overfitting to assert statements is a phenomenon they have also observed. And this is an example where we have an if statement for this case. Uh, um, and I'm assuming this is the biggest model. I'm not sure which model outputted this, but I'm going to assume it's the biggest one because the other figures are. Sampling strategy is critical for good performance. Um, and they did a study with BlueScore, and they found that synthesis performance, the correctness of a solution, doesn't correlate as well with BlueScore, which is generally used for code generation evaluation. They also investigated their dataset. Their pre-training and testing datasets have minimal overlap, which is good. So, and here they do, I haven't read the section yet, so I'm going to just not try and present it. I wanted to go over this section though. They have qualitative examples here. Highest performing problems are simple and common. Lowest performing problems are multiple constraints or multiple subproblems, specialized math problems, problems that have a more common sibling with keywords. So two problems that have similar similar keywords in the NL text, but they try to do different things. Okay. This is what is particularly interesting for me. Probably let me zoom in a little bit more. Okay, hopefully that's clear. Right. So this is where the authors try to study the model's ability to kind of interact in a dialogue form with a human user to generate code, which is what we can call conversational programming for today. And so here's a specification from the user. Human is providing this description. The model needs a few-shot example. The human gives them one example, similar to the form, an assert statement, similar to the form in the MPP dataset. The user provides, the model provides an output, which is incorrect. It fails this test. Human provides feedback. So feedback to the model is here, and then the model fixes the problem. And I think this is really cool. And here on the figure 13, they do a comparative analysis of how many dialogue turns does it take for the model to complete the task. And we can see about 30% requires 0 dialogue turns. Like the user just gives the description and the model generates the output correctly. And then 1 is probably 1 assert statement, and then 4 we get about above 60%, 65%, which is about a couple of hints, 2 or 3 hints. And here they do qualitative analysis on the dialogues. So these are more complex or more lengthy dialogues with more human turns. Here the human gives a hint, it fails. The highlight in here is it is underspecified. So the user here is not specifying enough information. So they're adding in more information here, descending order, because it wasn't mentioned earlier in the NL description. But here, the text on the right is more complex example. And the user is giving hints. And so here we see like two different types. And that kind of dialogue form really helps humans kind of think through what they need and add in as they go. Okay. I will skip to program execution results. Few-shot execution performance is poor. I think, sorry, let me just make sure that we're going through this properly. I actually haven't gone through this section deeply yet. I just skimmed it. This is the section where they try to predict the program output is my assumption. But I just want to make sure that's right. In this section, we investigate the extent by asking them to predict the results of the ground truth on test inputs. Okay. And these are the questions. Can models execute Python functions? How does the execution performance depend on what the information is in the prompt? How does fine-tuning on execution task impact the performance of execution? How does fine-tuning on execution tasks impact the performance? And so with few-shot, with the input and output examples, given the ground truth program, the model is tasked with predicting the output. And where's the table? There it is. And here are this is the ablation. And we notice that at max, with few-shot, we get 28% of predicting the correct output, which is vastly different from generating the right code around 60%, right, for this data set. Fine-tuning and execution slightly improves, but still, it's like, it's almost similar. Okay. Fine-tuning on execution has small effect on synthesis performance. It's a good title. And I haven't gone through the other dataset results, but they have a lot more. It's this. Let me go through highlights. Few-shot accuracy is 33.4%, and when fine-tuning, we get 81%. So drastic difference here. Okay. I will pause. I know like I moved around quite a bit, but these are related works. Yeah. Admittedly, I didn't have enough time to go through the entire paper, and that's why there was a lot of like, psst. But yeah, I'll stop for now. Those are like the main points.
No worries. It was a ridiculously long paper.
Yeah.
And they did a ton, but I mean, I'm very excited by this paper, especially the dialogue part. I mean, sort of codex paper took the wind beneath their wings on the other stuff, I feel like, but the dialogue part was extremely interesting. And I wonder, since they showed that it could use this sort of dialogue portion, I wonder if doing something for the syntax errors, if like they did the dialogue with the output from like the compiler or the not the compiler since this is Python, but the output of the program failing, if that would help the model fix those syntax errors similar to how a human does, where they try running it, they get a syntax error, um, and then they look at the line of code and they change it based off of the stack trace. I wonder if a similar sort of feedback loop could be done in this sort of dialogue system that they have.
Yeah, that might be interesting. They haven't described like if they tweaked the model in any way. Well, I'm not going to claim that because I haven't. I need to read it more thoroughly, but um, or maybe it's in the appendix. I haven't gone through the appendix. Yeah. So looking at this example here, you're wondering like the test fail here, and or maybe there's a syntax error in the code that the model generates or the human generates or types.
In the one that the model generates. So say
Mhm.
that they're missing like a comma or something like that. Because like the biggest issue that they said I think was that the model made syntax errors or something like that. Um,
Uh, it's runtime errors.
oh, runtime errors. Okay.
Mhm.
So maybe if they like gave that output of the which test failed or something like that,
Mhm.
maybe the model would be able to incorporate that feedback. But I was also just thinking of like if you could just give the model the stack trace. I know it's huge, so maybe you'd cut it down to like just the important bits of the stack trace, sort of like what humans do. Um, but perhaps as a dialogue, giving that back to um, the model, basically just saying, here was there was a syntax error. Here's the stack trace from it. Use this to fix your code or something like that.
Yeah, that's a really good point. There are quite a bit of works on. I think this is a notable one off the top of my head.
Yeah.
uh, this one. Wait, break it, fix it, semantics. I need to like stop doing this. This one, program repair. There we go. Uh, okay, so there is some work in automatically fixing bugs in codes given some error, mainly compiler errors. And they do this paper in particular does it in an unsupervised way. There are ones that try to do it using machine translation and so on. Um, but yeah, incorporating some sort of a bug fixer might be cool. Um, and maybe like learning more about the test cases. Like maybe each test case is testing for a particular bug or a particular logical error or runtime error, right? Um,
Yeah.
maybe informing if there's a way to learn from the test cases themselves. That might be really cool. Yeah. Anyways, I think that's really cool. One of the things that I'm interested in is like whether like these models can help like people learn about their code a bit more. So like imagine flipping it, right? Imagine the person is writing code and they have an error. Um, would the model be able to give them hints? I think that's something that might be really interesting. Um, I can't imagine how much labor it might take to curate a data set for that, but that might be really interesting. And it can have quite a bit of applications for conversational AI, being able to guide a human through a complex task like programming. Okay, yeah. But again, it would require the models to understand code, and we're not really there yet. So, but also like there's the debate of like, do they need to predict the output? Like, I guess predicting output does constitute some sort of understanding, but the purpose of this project or like this model wasn't to understand execution or find bugs. It was to generate. It was causal language modeling. My assumption would be, or at least masked language modeling. Since they just just cited the regular transformers paper. I don't know how they pre-trained the data. They don't have details. Maybe it's in the appendix and I missed it. Sorry, someone else. Any other thoughts?
I was just going to say that this sort of brought up a good way of, I wonder if it could be the reverse for this dialogue. So it's the human writing the code, and it's the model giving examples of how it's essentially trying to point the human to writing the code better for almost educational purposes. I wonder if that would work for these types of models. Probably not, since they aren't able to sort of, predict what the program's going to output. But I feel like that might even be somewhat more useful. Is to sort of there's been a couple projects on the evolutionary Discord about doing code reviews. So essentially trying to do that, but more even in a basic sense for like when a student is trying to learn how to program.
Yeah, that might be really cool. And I wonder, like, yeah, maybe like I can ask you about that project a bit after we're done. It might be interesting. I might be interested in looking at it more. The one about code reviews.
Interesting that both in codex and this paper, the authors mention that beam search doesn't work for this kind of problems. And but in the apps paper, so the paper which introduced apps dataset, I think the results were generated with beam search. So maybe it's not like it doesn't work. It's how you tune it, right? I don't know. So here they mentioned that the beam search mostly fails because of repetitive outputs, and that is also a problem in all the like natural language generation tasks, and there are different workarounds for that. So yeah, I wonder if it still doesn't work when you apply those, or because like intuitively, so the beam search should work better for this kind of task when you need to produce very concrete results rather than just something that sounds reasonable, right? And but it empirically it's not the case for both codex and this paper.
Yeah, interesting. Torsten, maybe do you have input on this observation? Torsten recently published a paper on Picard. You can also talk about that if you'd like.
Sorry, I wasn't sure if you were talking to me. Hi. The experience I had from producing SQL was that, or at least for the models I used, which were T5 models mostly, Beam Search made the vanilla models worse a little bit. So just doing greedy recoding gave slightly better results. But beam search was essential for constraint decoding, which is what I focused on, where the goal was to make sure that the model's output is not only syntactically, but also, well, you could say grammatically or logically correct. But this is a whole different story, right?
Mm-hmm.
This is typically not what people are after when they do beam search. And there's no mechanism beam search that would encourage this per se. But what we did was we added additional components that rejected productions that were deemed invalid.
Cool. So that's kind of similar to, I guess, the energy-based model, where I'm assuming like
Yeah. This was there a reading club on that one? I think we may have skipped it. But that energy-based model, they actually did this during training, or they had like an additional sort of reinforcement learning approach to how can we take an already pre-trained or fine-tuned model on a code generation task, and then sort of augment it with the ability to create more correct code without destroying the model, right?
yeah,
and
yep.
and we when we approached that differently, so we didn't like with the method we came up with additional training is not needed. So all the mechanics happen at inference. So you bring your model, the model is unchanged. We just force it to do more correct code.
Cool. Yeah, that's really good. How about inference time? Is it affected? I'm curious.
Slightly. Of course, if you go up from sampling or greedy decoding to, say, beam size 4, you take a performance hit, right? And especially if you have like large models, that may be a price you are willing to pay. But then on the other hand, the improvements were just significant, right? So like if you have, I mean, it depends on what sort of model you start with, but let's say a T5 large makes a lot of mistakes, and there it really pays off and can give you like a performance boost of like 10% or so on the data sets we tested it with. And you don't pay that much of a price. So I think one number I can remember now without looking at this paper was that I think with T5 3 billion, which barely fits in a 32 gig GPU, right? And beam size 4, I think it for like the data set we worked with, it took like I think 2.6 seconds or so on average to produce an example in the development set. And with that method active, it took 3.1 seconds or so. So there is a performance penalty, and it would potentially be interesting to sort of like understand where that additional time is spent. And I didn't do such an analysis, but if I had to guess, I think it is it's mostly latency, because the checker for whether or not the token is valid is implemented in a different language. It's not Python. And for that reason, we had to resort to an RPC transport between Python and Haskell, which is the language in which this was developed. So, and that has latency. So I think this is actually where most of the time is spent, because the Haskell code is very fast.
I see. Good to know. Yeah.
Yeah, so I wonder, it sort of brings up an interesting debate. I wonder, like, should we be trying to train inherently into these models the sort of, only generate syntax correctness, only do this. At training time, or whether or not what our main focus should be is on making sure whatever they do produce is like correct, is compilable, doesn't have bugs, and so I wonder if this like sort of like beam search pruning idea, it could even be extended also to like doing bug checking also for the different beams, to get rid of those as well. And if whether or not that's sort of what the future direction should be towards, or whether or not it should just be sort of baked into the model during training.
If you wanted me to comment on it, I would say definitely.
Yeah.
It seems like you could potentially try to address this with like data augmentation, right? But I mean, it seems that the method I've been studying there, I mean, just use it, kind of like, I mean, I've did this now in SQL, right?
Mhm.
And it definitely takes some time to develop this for SQL, right? And you would have to develop it for target DSLs or target languages, but you only have to do it once, right?
Yeah.
But it is an investment you would have to make. Let's say you make that investment, then you can just use it, and it works. And it works with any language model, right? Whether it's now GPT-3 or T5 or I don't know what, because they all work the same way. You produce also regressively token by token, and in that case, you would be able to use beam search and therefore also this method. So it works. There's no coupling between training and inference in that sense. Right? So like this method doesn't need to be adapted to your model, nor does the model need to be adapted to this method, which makes it quite flexible.
Yeah, I like that, especially since adding in all of the extra checks to make sure that the model is generating the correct, constraining the training, I feel like would be such an extra overhead than just constraining the inference part, since training is where most of the computation happens anyways. So to me, it also makes sense to sort of almost, sort of use the trained language model as the starting point instead of trying to bake in all the extra knowledge about compilers and compilations or bug stuff, and just focus on guiding the model at inference time so that it produces correct programs.
Additional thing is like that if your mind changes, right? So like if, for instance, let's say you had some business rules, right? And I don't know, maybe they're not actually etched in stone, right? Maybe they're subject to change, and you would need to enforce them and their changes. Then it's certainly easier to do that in an algorithm that is only affecting inference than one that actually forces you to retrain your big language model, right?
Yeah, that's actually a very good point. Yeah, you want to not have to retrain the model multiple times when all this stuff changes. So yeah, that's actually a good point.
Okay. Any questions for me? That was really good.
Did you like the paper?
Oh, I did. Yeah, I still need to chew on it a bit more, to be honest. Like, I haven't went through the appendix. And I haven't gotten through the other set of results for the MathQA dataset. I want to go through them. So yeah, and there's also like the misconceptions that I had about like the sampling.
Mhm.
I want to go back and reread them. Like this figure didn't make sense to me. And I think Yeah, I think the percent of samples here didn't make sense to me, especially since they say like we only generate a single sample with greedy decoding. So that threw me off. But yeah, there are a couple of things I want to like go back and kind of try and understand.
Yeah, I'm gonna have to
But yeah,
definitely read through this paper.
yeah. And I'm also interested in like how they set up their conversational programming study. Like, I haven't gone through text explaining how they trained the model to like kind of speak to the human, since it's not mentioned in the data set, right?
Mm.
Um, maybe few shot was enough for something like that, but I'm not sure. Maybe it's in the appendix. I mentioned stuff in the appendix, but I haven't gone through the appendix yet.
Are there any models like publicly available? I see the link to the tracks repo, and do they have the models?
Yeah, I don't think so.
Yeah,
Let me see.
I don't think they released the models either. It's so sad.
Yeah, they don't even have a description, a clear description of what the models are. They're just like, oh, we use transformers. They didn't even describe the pre-training function, or like, obviously they didn't. Yeah, nor the data they trained on. Yeah,
The tracks library is kind of a bit messy still, I guess, because it's kind of not really a big group of people working on it, I believe. Yes.
Mm.
So.
Yeah. They describe
And
uh-huh.
if they don't release more like open source code, then it wouldn't change. But I think this kind of this group was quite good in open sourcing their stuff, I guess. But yeah, maybe it's not true for this kind of models.
Yeah, I wish there was. Like, the only code they release is like this, where they convert the Q&A, math Q&A dataset from DSL to Python. That's it. They do release their datasets, so I'll give them that. The ones they worked on.
I believe.
Yeah, but it's really fresh, so maybe it just needs some time to do.
Yeah.
I really.
Was this an EMLRP submission?
I
And
don't
did it
know
get
where they
accepted?
submitted to.
I don't actually think it has been yet. I think they just released it sort of like OpenAI on archive. But anyways, y'all, I'm gonna have to get going. But I really enjoyed the presentation, Irfan, and the discussion sections, y'all. Those are always the best.
Thank you guys for joining. It was really good.
Thanks so much for the presentation. I enjoyed that a lot. I was mostly silent, but I listened to every minute of it, and thanks very much.
Thank you so much. Yeah, I appreciate it. I hope to learn more and present more in the future.